we're going to talk about the magnetic field inside a toroid. I don't know if it's one or two R's, so I'm spelling it with a single R for funsies. All right, a toroid. So I'm going to draw what I think is a good representation of a toroid, but what's hard is a toroid is it's like it's like perfect day. It's a donut. So it's excellent that today is toroid day. Nope, not a square. Never had a donut. No.
No, I haven't had one yet.
Do you like donuts?
No, it's okay.
No, you can have my donut.
No, it's okay.
You've had a hard day. Besides, it's got little hearts on it.
Thank you.
Please, enjoy. Besides, I hear Miss Casping has a whole bunch. So. All right, so I'm defining a space, but I want you to imagine that a toroid is like a solenoid that's been turned into a circle. So this represents kind of the core of the toroid, because you'd have to have something to wrap the wires around. Does that make sense? So imagine our wires, say, coming in from this side, would wrap around the toroid. Want to do it that way? I guess I do. Come on, Mr. Shelton, draw better. I'm doing the best I can. I'm not a good drawer. There's all these people watching me, and it's making me freaked out. Actually, none of them are watching me. They're all watching their papers or their iPads. It's kind of weird being in teaching. It all started with hearing you guys be scratching on your paper, and now it's all these tapping. It's just weird. So, there. Does that look good? Do you guys see it? Does that make sense? Thank you. I do my best. So this is a toroid. Now, one thing we're gonna learn is that we're missing a piece of the picture, but this is a part of it. A lot of times, what you might see, like if you were to break open one of those wall warts that I'm talking about, the thing you plug into the wall to plug your USB cable into. I don't know if there's a better thing to call it. Those are an AC to DC converter. And one of the things that will be inside of them often will look like a toroid, or maybe even just a circular magnet with wire coils around them. They're probably not a toroid. They're probably a transformer. A transformer is different than a toroid, but it also is often in a circular shape like this. But this is a toroid, and let's go ahead and put the current direction like that. So the current's kind of going in this way, which means that every wire that we see, which is on top, has current going in this direction. Does that make sense? I see a problem with the way I drew this. I want to fix it because I'm not a perfectionist, but I play one on TV there. So if you're to use your right-hand rule, and I know we're kind of doing this on this nice flat, picture, but if you use your right-hand rule, and I'm going to use the curl rule, when you put your thumb in the direction of any one of those arrows, your fingers would curl in this direction inside the toroid. And these yellow arrows kind of are the direction of the magnetic field that would exist inside our toroid. All good? Now we're going to use Ampere's law to find the magnetic field inside the toroid. Now, I think it might be better for us to kind of, expand this and make a better picture where we cut away the wires and have into and out of, but I'm not sure that's really a necessary activity. So what I'm going to do instead is consider a Amperian loop that is inside the toroid, but that is concentric with the toroid. Remember, we need an Amperian loop that goes around some of the wires so that we can use Ampere's law to get a feel for the magnetic field. So I'm choosing an Amperian loop that's inside the toroid, and it is drawn in such a way that it is concentric with the toroid. Does that make sense? Because I'm going to say that it has a radius of r. Are we ready to begin? There's not much to this proof or this derivation, as there hasn't been much with any of the derivations that use Ampere's law. They're just not particularly complicated. So we'll have mu naught I enclosed equals a closed line integral around our Amperian loop. Now again, a couple things I want to do. I don't see any easy way to break this loop up into pieces. I think we're going to go ahead and just go around this entire loop. Does that make sense? I want to start evaluating things about the dot product. So let's start with the dot product itself, the cosine portion of it. If I take this and rewrite it as b times ds times the cosine of theta, that theta is going to be the angle between our ds and our magnetic field. So if I were to zoom in to a section, our ds is a piece of our Amperian loop. That's ds. And at this instance here, the direction of ds would be tangent to our curve. But our magnetic field would also be in the same direction as ds, as long as I integrate in this clockwise direction. Does that make sense to all of you? So I think it can be easily said that both ds and the magnetic field are in the same direction at every point inside the loop. And because we can say that, I think with pretty easy confidence, we can go ahead and evaluate the cosine to be theta of 0 degrees. Now, the other thing I'm going to evaluate is I want to take a look at the magnetic field and I want to ask a reasonable question. Do we think the magnetic field is different at different points along the loop? In this case, I'm talking about the Amperian loop. Meaning, if I look at this, is the magnetic field here likely different than the magnetic field here? Or do we feel as though the magnetic field is going to be the same along this particular path? I think too. I think it'll be the same along this particular path because we are the same distance away from the center. So I'm going to go with the magnetic field is a constant everywhere along my Amperian loop. So all I really need to do is sum the length of the loop. Now, I could break this up into r d theta, but can we all agree that the length of this loop will simply be the circumference of the loop, which is 2 pi r? So this side will be b times 2 pi r, the circumference of the loop. Just remember, if you're trying to take notes and you're trying to be careful about what each step is, I'm saying what each step is. But it would be great if off to the side you were talking about what we did to go from here to here. Right? If you really want to understand this and be able to do this in a problem that might not conform as simply, what questions did we ask? Well, when we went from here to here, this was, go ahead and expand the dot product. All right? That's what we did there. And here, evaluate the cosine. Well, evaluate the angle, theta, between B and ds. I don't have room for that, but you guys could probably do that. This step was, is B uniform along ds? Right, that was the question I asked. Is B the same value along every part of ds? Now, in our last example, that was not true. Sometimes b was 0, sometimes b was the same. We broke our integral up into separate integrals, but we still asked that question each time. And then our last step was, in this case, the summation part, this. Summing the integral of ds is just a length. And that's all we're doing. I said, we are really trying to skip doing actual integration on this stuff whenever we possibly can. But that leads to that particular answer. And then our left side is still mu naught I enclosed. So all we're left to do now is come up with a way of expressing I enclosed. And that's what we'll do next. Let's look at our picture here before I kind of zoom in on it. If we just look at our picture, our Amperian loop actually encloses all of the current loops, right? All of the coils. So all I really need to know is how many total coils there are on this toroid. So when I look at evaluating this, it's going to be the number of coils times the current in the wire. So this is going to be the number of coils. It's not a coil density like we talked about with the solenoid. It's just the fixed number of coils in the toroid. And again, that's going to equal B times 2 pi r. So as a last step, we just want to solve this for B because the idea was to get an expression for the magnetic field inside the toroid. So we'll solve this for B, and we'll get mu naught n times I over 2 pi r. Now, I know this looks like a different thing that we solved earlier, but remember, this is a very specific geometry. This r is not how far away from a particular wire we are. This r is the radius of the Amperian loop. So in our particular toroid, our r can only extend from the inside of the toroid to the outside of the toroid. But it does tell us that we don't have a uniform magnetic field inside a toroid. We have a magnetic field that gets weaker towards the edges and stronger towards the center. Now, I'm sure that there's some uses for this, and there are some direct applications for how a toroid has been used. If I have a long current carrying wire, you should be able to tell me what the magnetic field is from this wire if I am a distance z away from that wire. Right, because you memorized it. So what is the magnetic field at distance z away from my wire? Go ahead. Mu naught I over 2 pi z. Right? So this one gets the pi, right? An actual circle of current doesn't, but this one does. So based on my drawing, would that magnetic field be into or out of the board? Right hand rule, so raise your hand if it's into the board. Raise your hand if it's out of the board. Well, it can't be any of the other choices, so you guys who didn't raise your hand, boo-hoo, but it is out of the board. There's a magnetic field there of that size. So let's say, for fun, that I have let's go ahead and make it a square loop of current with a current that's going counterclockwise in the loop. And let's say, for fun, the square has side length z. Does the current loop experience a force? It's a yes or no question. What do you think? We did talk about like currents and unlike currents and what they do. Do like currents repel or attract? Like currents attract and unlike currents repel? Okay. I see at least one of each of those. Do you? And then I see two others. Don't you? All right. So I want you to think for just a moment. We'll go A, B, C, D. There are 4 wires here. A to B, B to C, C to D, D to A. Can you come up with an expression for the force on each of those wires? I'll wait patiently as you guys discuss. Like maybe you have forgotten everything. Let's remind ourselves that the force on a current carrying wire is I L cross B. You'll need that information. The next thing is, I think this goes without saying, but the magnetic field from the blue wire is out of the board everywhere on this side, isn't it? I think that's going to be important. So when you're looking at, say, from A to B, using just F equals IL cross B, the cross product is between the direction of the length and the direction of the magnetic field. These are vectors. So we can just right-hand rule parts of this, can't we? Let's start with the simple stuff. Got my right-hand rule here. I'm going to point my pointer finger to the right, because that's the direction of the current from A to B. I'm going to rotate my middle finger out of the board, or upward if you're using your paper, and I get a force on this wire that is this way. Can you do that for each of the things here? So do we have this one? Right? Is that what you get? Just IL, I'm just cross producting. I'm not even looking at size yet. Just doing the cross product. C to D, what direction should I draw that arrow? Up, down, left, or right? It is up. Thank you. And look, if I'm doing this and you don't know what I'm doing, you should stop me. There's 12 people in the room. You can't talk in front of 12 people. Well, 16. You're going to have big problems. And what direction should I draw that arrow from A to D? Up, down, left, or right? Left. All right. Now, how many of you think, because of the way the arrows are drawn, that the net force on the loop is 0? Anybody? It does look like that, right? Except for one thing. Is the magnetic field from the blue wire uniform? Or does it change? It changes. It gets weaker as we get further away from the blue wire, doesn't it? Which means this magnetic field is the field from the blue wire acting on the loop. Correct? So I think C to D is further away than A to B. Now, I also think that B to C and D to A must experience the same size force because they are exposed to the same size change in magnetic field. So I think this component and this component will be the same, and those will cancel out. But I think this force is going to be stronger than this force. So the force for A to B has got to be I, Z, mu naught, I, oh, capital I. Come on, Miss Shelton. Don't make a mistake here. Capital I over 2 pi Z. Any question of where I got any of that from? Where the lowercase I is the I in the loop. And my force from C to D, well, that's going to be I, Z again, because Z is just a length of wire, and that's still Z. It's a square of side length Z. But the magnetic field up there is mu naught I over 2 pi times 2Z, because I'm 2Z away. Right? So if I subtract those two, because they are in opposite directions, I will have the net force on the wire loop. this wire loop is going to be pulled towards the other wire. Simple enough. If I was to reverse the current, it'd be pushed away. This is another way to create mechanical work from a electrical system. This would not serve as a motor so much, but you could imagine turning a current on and having something expand a little bit or contract a little bit. Could you find that useful? There's probably a lot of situations in which that could be a useful thing to do. Now, this would be tough because you'd also have to have this maintained current here. So it's not just one current, it's a couple of currents. And although this looks isolated, it doesn't have to be. Right? That can be generated from something else. But this is another way to cause a force on an object, and clearly a net force that could be a little bit of a contraction or a little bit of reduction. There's another little thing. And this is not a thought experiment. Every time we do one of these, there's some way of making practical application, and practical application of this stuff has happened. And so just imagine all the little things that move in your life or that require movement. You know, finding a way to get something small to move or something to have a small bit of force act on it is something we do all the time. And doing it electrically means we can turn it on and off with a switch. It's one of the advantages here. Now, there's one more thing I wanted to talk about, and that was the magnetic field inside a current carrying wire. We're not going to get to that today, so that's going to have to be a next week kind of thing. But at the same time, you should try it. I'll throw a sample problem out there at you guys. Take a look and try it. It's not a hard calculation.